Bn equals 1 by L integral 0 to 2L f of x sin pi n x by L into dx, where f of x equals 2x minus x square and L equals 3 by 2. We have the upper limit 2L equals 3. Here we will perform the integration using integration by parts. We have the second term obtained as minus sine 2n pi x by 3. When you give x equals 0, this function will become sine 0 which equals 0. When you give x equals 3, this function will become sine 2n pi into 3 by 3 which becomes sine 2n pi which equals 0. Therefore, only these two terms will contribute non-zero answers after application of upper and lower limit. When you give x equals 0 here, this term will become 0. When you give x equals 3 here, it becomes 3 by 2n pi multiplied to 2 into 3 minus 3 square multiplied to negative cos 2n pi which becomes 9 by 2n pi multiplied to cos 2n pi. We have cos 2n pi equals 1. Thus, when you give x equals 3 to this term, it becomes 9 by 2n pi. Here, this denominator 2n pi by 3 the whole cube becomes 8n cube pi cube divided by 27, and this when taken to numerator as its reciprocal, we will get minus 2 multiplied along with 27 divided by 8n cube pi cube which becomes minus 27 divided by 4n cube pi cube. When you give x equals 3 to the function cos 2n pi x by 3, it becomes cos 2n pi which equals 1. When you give x equals 0 to the function cos 2n pi x by 3, it becomes cos 0 which is again 1. Since these two values are 1, this term will also become 0. Thus, we are left out with bn equals 2 by 3 times 9 by 2n pi which equals 3 by n pi. Having found a0, an and bn, now we can write Fourier series representation for f of x equals 2x minus x square. This is the Fourier series representation obtained. Now we wish to prove the result 1 by 1 square minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square plus etc. equals pi square by 12. Here in the LHS of the result to be proved, notice that all the denominators are square denominators. When you give x equals 3 by 2, this sine function will become sine 2n pi into 3 by 2 divided by 3 which becomes sine n pi which becomes 0. When you give x equals 3 by 2 to this function, it will become cos 2n pi into 3 by 2 divided by 3 which becomes cos n pi which equals minus 1 the whole raised to n. From this we come to know that when you take the choice x equals 3 by 2, this term is disappearing and this term with n square as the denominator exists. Therefore, x equals 3 by 2 is the most appropriate choice which will maintain square denominator n square. When you give x equals 3 by 2 to the function f of x, it will become 3 minus 9 by 4. On taking LCM, it becomes 12 minus 9 divided by 4 which becomes 3 by 4. Here we have this RHS. When given the value x equals 3 by 2, it reduces to this format. From here, 9 by pi square can be taken outside summation because it's just a constant. Now we have the equation 3 by 4 equals minus 9 by pi square multiplied to summation n ranges from 1 to infinity cos n pi divided by n square. When you multiply both sides of this equation using pi square by 9, we will get the equation minus summation n ranges from 1 to infinity cos n pi by n square equals pi square by 9 multiplied to 3 by 4. We have pi square into 3 divided by 9 by 4 equals pi square by 12. When you give different values for n here inside the summation along with the minus sign, we will obtain, considering cos n pi equals minus 1 the whole raised to n, the summation is equivalent to 1 by 1 square minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square plus etc. For example, give n equals 1. Then we have minus 1 multiplied to minus 1 the whole raised to 1 divided by 1 square which becomes 1 by 1 square. When you give n equals 2, we will get the term minus 1 multiplied to minus 1 the whole square divided by 2 square which will give the term minus 1 by 2 square. When you give n equals 3 here, we will get minus 1 multiplied to minus 1 the whole cube divided by 3 square which becomes positive 1 by 3 square and so on. And we have the RHS already obtained as pi square by 12. and thus we arrive at the required result to be proved.